Okay, welcome back. So this is part 2 of the lecture on section 3.8, exponential growth and decay. So in the first video, we were talking about exponential growth and the law of natural growth. So functions that satisfy the law of natural growth and happen to be increasing functions are growth functions. Decay functions are also considered exponential growth functions. However, they are decreasing, not increasing. So in this video, we're going to talk about decreasing functions. In particular, we're going to be talking about radioactive decay and carbon dating. We'll do an example. So we're going to use a couple of facts from chemistry. So the first fact we're going to use is that the relative decay rate of a radioactive substance is constant. And, as I mentioned, it's also negative. So what does that mean? When we said that when a relative growth rate was constant, that meant that the function satisfied a differential equation that said that the growth rate, or the rate of growth, was proportional to the size of the function. So here we have a relative decay rate. It just means the same thing, except it's a negative constant instead of a positive constant. It still means that the function has to satisfy that differential equation, that the rate of decay is proportional to the size of the quantity. So if m is the mass of this radioactive substance, then the rate of change of that mass with respect to time, dm dt, is proportional to the mass, or is equal to some constant times that mass. I'm pausing because I just got a message from... Okay, I just got a text message from DBC Police saying that students and staff are having conversations about the graffiti. And in case you haven't heard, there was graffiti threatening the use of firearms. So the message says, if you have any information about the graffiti or the suspects, please call the Contra Costa Community College District Police Silent Tip Line, 925-229-6464. The Police Silent Tip Line, 925-229-6464. Okay, back to exponential decay. So the second thing that we're going to use from chemistry is the definition of half-life. The half-life of a substance is just the time that it takes for half of the substance to decay. So it's just how long is it going to take for half of the substance to go away. So, for example, carbon-14. When an organism dies, the amount of carbon-14 begins to decay. The half-life of carbon-14 is 5,730 years. So carbon-14 is a radioactive isotope that scientists use in carbon dating. So we know how much a living organism contains. We know how much C14 a living organism contains, and it remains constant while the organism is alive. But as soon as the organism dies, it starts to decay. And we know it takes 5,730 years for half of it to decay. So if we discover a fossil, or say a murder victim, we can measure the amount of C14 that's present in this no longer living organism. And we can determine how long ago it died by measuring the C14. So let's do our first example. This is number 2 on that handout that I hope you printed out. If you didn't print it out now. You can pause the video or just copy down the problem. So the problem says, suppose a piece of parchment has been discovered and it contains 74% as much carbon-14 as does living plant material. How old is the parchment? So parchment is paper made from a plant, a leaf. So we find a piece of parchment and we measure the C14 and discover that it has 74% of what it did have when it was alive. So we're going to determine how long ago it died. So let's call y of t the amount of radioactive C14 present at time t years after the plant died. So then y of t has to be equal to y of 0 times e to the kt, where y of 0 is the amount present when it died. So that's the amount that it had the whole time it was alive, and then as soon as it died, it started to decay. So it's the original amount, y of 0. We don't know what it is. So also k is just some constant. We know k should be negative, right? Because we know this y of t should be a decreasing function. So that exponent should be negative. Okay. So first we got to find k. To find k, we're going to use the half-life of the radioactive isotope. So we know it takes 5,730 years for half of the C14 to go away. So half of the original amount has to be equal to the original amount times e to the k times 5,730. So we plugged in 5,730 for t, and we set y of t equal to half of the original amount. That's what 1/2 y of 0 means, half of the original amount. So we're going to try to solve this equation for k, and then we'll have our function. So here's the equation again. We're going to try to solve it for k. So first of all, I've just divided both sides by y of 0. That was just a number, a constant. It appeared on both sides. I could divide both sides by it. Then I take the natural log of both sides. So the natural log of 1/2 has to be equal to the natural log of e to the 5730 times k. So the left side is still natural log of 1/2, but the right side then is just 5730 times k, because the natural log of e to the x is just x. And now I just divide both sides by 5,730. And so there's k. Does that look negative? You should stop and think about whether your answers make sense. So we're not going to put it in our calculators. Never do that, because you'll just get an approximation. So we're going to leave it as an exact answer, and then we're going to use it in our function. So don't put it in your calculator, but you should be able to tell that this is a negative number, because we can rewrite the numerator as negative natural log of 2. And we know natural log of 2 is a positive number because it's greater than 1. So this is a negative constant. K is negative. Great. So now we have our function. Y of t is equal to y of 0 times e to the negative natural log of 2 over 5,730 times t. That's the function. And we do not put k into a calculator. we leave it as an exact number because that helps us keep from getting rounding error every time we do a calculation. So now I want to know how long ago did this thing die? So I have 74% of the original amount of C14, and I set that equal to the function y of 0 times e to the kt. And now I'm going to solve this for t. So once again, I can divide both sides by y of 0. So I have 0.74 equals e to the negative natural log of 2 over 5730 times t. And now, once again, I can take the natural log of both sides to bring I want to bring the variable down out of the exponent. So take the natural log of both sides. And on the right, I can rewrite that exponent, or I can just bring down the exponent. And now I can just divide both sides by negative natural log of 2 over 5730 to get t. So t is the natural log of 0.74 times 5,730 divided by negative natural log of 2. Now we want it to be positive, right? We want it to be t years ago that it died. Is this positive? Yes. We can tell it's positive because the numerator, the natural log of 0.74, we know that that is a negative number because 0.74 is less than 1. So the natural log of 0.74 is negative. So we do have a negative over a negative, so we do have a positive number. After we put that in a calculator and round it, we get 2,500 approximately. And so the answer to the question is the parchment is about 2,500 years old. It's made of a plant that died about 2,500 years ago. Okay, so there's one more video on section 3.8, but I will conclude this one now.